Okay, so as I was saying, I'm glad to be back in ICTS and standing in front of this Guinness Book of World Record holder for the longest green board in the world. And this happened because of the organizers, so let me thank the organizers for inviting me over here. So today what I'm going to talk about is basically the phase space of dark matter in Milky Way and local galaxies. And note that I have sort of under quotation marks, I've said the observed phase space of dark matter. And that's because typically when one talks about phase space of dark matter, most of the work that we see in the literature is from simulations or theory. But this is going to be from observation. So we are going to look at how the density, of course, is there, but how the velocity is also can be seen from observations. Okay. So this has been sort of I'm going to show mainly for the students over here, and this is a culmination of basically showing results from many years of work, mainly by students who work with me. At present, Manush is over here, and then there have been past students. So I'll basically tell you what people did. Okay. So let me try to say why we want to look at this phase space of dark matter. Okay. So this is a slide that I stole from the internet. Of course, this is why we want to do this. And the reason is that if you want to know what is dark matter, it can be many things. We don't know what it is. And what we want to look at is, can we identify a region over here in the mass and the interaction plot? And if we can identify a region over there, then maybe we can say, okay, maybe dark matter is this. Now, to do that, people, of course, try to do different kinds of experiments. There can be direct experiments, direct detections. There are indirect detections. There may be in collisions. So you'll hear about all of them in this workshop. And the idea is, if you get something from this, and then you can relate those to the map that I showed in the previous slide, and if we can sort of zoom to one region, then that is our dark matter particle candidate. So what we generally see, this is an example from direct detections, just a random choice. So indirect detections, you'll see these exclusion plots. So here again is the interaction cross-section. There is a mass, and you have different direct detection experiments, give you different exclusion plots. So basically it's saying that things which is above are excluded. And there's the same thing from indirect detections. Now, what I want to emphasize over here, which is often missed, is that in all these exclusion plots, there's an impact of phase spaces, spelling mistake over here, which is there. And you really need to note them if you want to be very accurate. At present, we are not at the stage, but we need to know this very well. Okay. So let me give an example with direct detection. So if I look at the direct detection of dark matter, this is a classic case of synergy in physics. And so here is a recoil rate, and people, so experiments determine the recoil rate, and from there they want to look at these exclusion plots. And if you look at this equation, what you see is something very interesting. So there is particle physics over here, so it's in green, okay? There is nuclear physics over here, there is detector physics over here, and there is astrophysics, it's galaxy physics over here. And if you look at the number of papers that has gone into using this equation, you will see people have spent a lot of effort in this particle physics, the nuclear physics, the detector physics. The galaxy physics, the astrophysics part is more naive over here, and that's something that one needs to improve upon. Okay? So if you take, again, a typical example of a paper which talks about limits, so this is the Lux data paper. You'll have a PRL paper, but you'll have a page of working on the uncertainties, look at uncertainties. But then over here, you can see uncertainties in the assumed dark matter halos are beyond the scope of this letter. And so it will be taken very simply. But we need to know that that's where the phase space of dark matter comes in. So what is typically assumed in the field when people are doing this direct detection or indirect detection? What they assume is these three things. First, they assume the density, typically, to be a single component isothermal sphere, okay, with a local density of 0.3 GeV per cc. This is a famous number, which is always taken. This came up in the 90s by Bahakal, and it has stuck, and people have gone beyond it and come back to it and gone outside it and come back to it. but we need to know how good it is, okay? They look at the velocity of dark matter, and over here, they assume it to be a Maxwell-Boltzmann, okay? And so this is a form, and it has some truncation. And then the third thing they do is that they assume that the density of the dark matter is smooth, so simplistic, or sometimes a very simplistic treatment of clouds. Now, neither of these three assumptions are right, okay? First of all, neither of these right, and also, if you want to change any of these, you better change the other because there has to be some self-consistency in it. So if you have to improve on them, you have to do it self-consistently. So that's where the phase space of dark matter comes in. So what I would claim is that the search for the particle nature of dark matter is deeply linked to our insight of the astrophysical nature of dark matter. Okay. So let's start with density. And this is something that the students have worked with me, Shayan, Aditya, Viraj, most of them have now passed. They're doing their PhDs abroad, okay? So how do you look at the density? We start by mapping the potential. I'm talking about a global potential over here. So what is a global potential? Why do I say it a global potential? So take the rotation curve. So this is, if you have to have tracer particles, it is rotating, okay? Let's say in the disk. So if a rotation curve, and then this rotation curve can be linked to the radial derivative of the total potential. Some of it comes from the dark matter, and some of it comes from the visible matter. It is very important to understand that this thing has contributions from both of them. So you should not sort of fix one of them or ignore one of them if you want to basically get the potential from the rotation curve. And this is also done very often. Now, this is, of course, near the disk. If you go outside the disk, so the non-disk region farther away from the center, then you can actually build a sort of a rotation curve by looking at the Jeans equation, use it to construct potential, and the potential you say, okay, a circle in that potential will give you an extension of the rotation. So people have done that, and we have also done that to construct rotation curve of the galaxy from the very center of the galaxy to the virial radius, or almost 200 kiloparsec of the galaxy. Okay. You can also do something different, which is also done, is can map the local potential by local kinematics dispersion velocity of the local stars. So this is slightly different. So in the global potential, you think of the disk, or think of some plane, and the stars, the tracer velocity is going like this. The local potential is over here. Here's the disk. So this is over Earth. You look perpendicular in this direction. And if you look at the dispersion of the stars, that dispersion velocity depends on what is the potential, local potential over there. So again, the potential is what is the dark matter amount and what is the visible matter amount over there. And so one can basically look at this vertical Jeans equation, okay? And it connects the gravitational potential with the stellar density. And so if you assume some symmetry, it's a local, so axial symmetry, you use cylindrical coordinates, and it's very simple assumptions of separability, exponential distribution of the stars. Basically, we know because the disks have exponential distributions, one can look at this kinematics. And if we can separate out the effect of the baryons, then the rest of the kinematics is due to the amount of dark matter. So that's how I connect local potential with the dark matter. So this is something that people have done as well. So over the many decades, people have been either doing this or the other, and they have come up with a different amount of dark matter, which you think is in the vicinity. Now, of course, one has to connect the density distribution with this kinematics or this rotation curves. So you can make it as complicated as you want. You take some density of the total dark matter halo. You take disk, maybe not one kind of disk, maybe two kinds of disk. You take dust, you take bulge, depending on how much the data you have, how much is your power to constrain your data. You can use a large parameter set, and then maybe these days you do a Monte Carlo Markov chain. But the important thing I want to point over here is that you should not put any strong priors. Again, why I'm saying this is that because people do it all the time, people put in strong priors. I have seen Nature papers where they are fixed baryonic densities and infer that there is dark matter at the center of the galaxy. I mean, if you do not fix baryonic densities, remember, everything is, what you can get is basically some tracers, some amount of kinematics of the tracers. I can always put one more, put one less. So you should not fix anything. You should marginalize and try to get it. So this is very important. This is something that the students should know. You should never put strong priors. People even have fixed things. People have said, that's like as strong as it can. You say, okay, this is the amount of baryons that we have. We know for sure. So the rest is dark matter. We don't know for sure. Okay. Now, so what is the local dark matter density? Is there a consensus? So if we look at pre-Gaia, and Gaia is a satellite which is revolutionizing the way we look at our Milky Way, then people have used rotation curves and global models of Milky Way and found dark matter densities in this region. The most popular is dark matter having 0.4 to 0.44 GeV per cc. Okay? As you can see, there is a large range of values that people have got. Okay? Then people have looked at local kinematics. Over here, the range of values is even more. Well, some of them you can say, okay, maybe very naive, some is better. You can argue about which is good or not. In fact, what is worrying, or what tells us that you have to be careful is that, for example, these people, Bovie and Tremaine, Monibidin, they look at exactly the same data sets, and they get very different amount of dark matter. And of course, both of them have criticized others in the way that they have done it. So, and then you go to post-Gaia, where the rotation curve is very well determined in the disk region. And so I'll give you an example. They've got one. So look, this is very much the Bahcall number that they have got. It's the error bars are like this. The error bars have gone down. Now, one thing to understand from over here is that we're still not there at a consensus. I mean, I can take another post-Gaia data with something else using Cepheid variables maybe, and I will get a slightly different number over here. And all this is happening because of many reasons, and I'll try to come to one of them one by one. So the first thing to understand is that, as I said again and again, what we are really looking at is a measurement of the potential. And over here is what I've done is that I've looked at the potential and divided by the rotation curve. Okay. And so if I look at as a function of the distance from the center, you see the contribution to the potential from different components, the visible matter and the dark matter. So the relative contribution to the total potential from the visible matter and the dark matter changes as we go from center to center. So for example, very, very quickly, if I fixed one of these, then I would get a different dark matter. If I fixed another one, I would get different dark matter. That's very important. So if we understand this, then one can actually go and see that in the literature, a lot of these discrepancies is because of the assumed visible matter, which is the surface density of visible matter. So people sort of assume or put strong priors. Sometimes they fix, as I mentioned, but sometimes you also put strong Gaussian priors. And so depending on what kind of priors you put, you fall in certain range of dark matter. There's one more thing which is interesting is that you also have to be very consistent with the data. So different people use data, and they are roughly divided into classes, which depends on what is, how they're normalized. So there's something called the local standard of rest. So if you change your local standard of rest, you can take the same measured data set and sort of slightly change the output data set. And there are the IAU convention of the local standard of rest. The Gaia gives you a local standard of rest, which is probably the best right now. And then there's a particle physics world, which uses a different local standard of rest. So if I go from one local standard of rest to the other, you're going to, for the same data, with everything else the same, you're going to get different constraints. So over here, there are different local standard of rest. And the most popular, which is this 0.3, which is this BT, which was this Bobby and Tremaine prior to the Eilers et al., which is also 0.3. They get 0.3 because this is their prior on the visible matter. They put a prior over here on the visible matter. So in this degeneracy direction, this is where they pick up. Okay. So what do you do? How do you break degeneracies? One simple thing to do is to combine your kinematics with your rotation curve. And why you do that? Because when you do the kinematics, Of course, you don't know what is the distribution of dark matter, but you have a better idea on the local visible matter. But we know there is a form of dark matter. That's our assumption. There is some distribution, some density profile of dark matter. The larger radii sort of constrains that density profile. So when you put in your rotation curve with your kinematics, you break this degeneracy that was coming when you're doing together. And so as you can see over here, this is the local region. This is where the kinematics is done. So this is because vertical, so I've flipped it. This is the Z direction kinematics. There are points of 30 bins in the Z direction. And there is a radial bins of 50. And as you can see, with different priors, I would have very, very different large radii behavior. But over here, I would still have the same kind of behavior. Okay. And so over here, these degeneracies, I will only be able to break if I have data over here. So when you have both data over here and in the Z directions, you break these two. So what happens if I use the pre-Gaia data? The first thing you see is that if I do kinematics, this is rotation curve, this is kinematics, they would have given you very different results. But then when you combine it, you get a tight constraint, and this is the tightest constraints on dark matter to pre-Gaia, which is this. This is less than the 0.3 fiducial dark matter value that we. So local means for direct detection, of course, we need to the dark matter density right over here. We cannot do that. Around a kiloparsec around us, let's say. So that's a local.
The number which will go to the dark matter detection.
Yes. So what is the average density? Of course, yeah. Yeah. Yes.
They're overlapping at like sigma.
I know.
Doing a bit. Like, why do you know that you can really therefore combine them?
So yeah, so this is something that I've thought about a lot of time. I mean, this amount of inconsistency and combining them, you know, so we all come from cosmology. You have seen that people have combined this like this in large scale structures also. So that's what I'm doing it. I mean, I would be very happy if they were closer. And the reason is that, you know, over here, this rotation curve, there is a lot of chance of a degeneracy. And over here, again, depending on what kind of LSRs you are using, that also changes stuff. And so all these things goes in. This thing becomes actually worse when you use Gaia. Gaia is so sensitive at certain region and so insensitive at certain region. It doesn't really. And so it makes these degeneracies slightly, stretches these things. And the idea is that once you have a slightly better data on the non-disk region of with the Gaia, which you're working on, maybe you will have a better consistency with these things. But at present, this is the whole point of we are error bars, whether you believe it or not, the error bars are better, but all the previous work. So there is no consistency, that's what I wanted to say.
All the other axes to this one, all the
No. Okay, so in comes Gaia. So what Gaia has done is that you can see it has improved the error bars very well over here. And this is why people have actually just used this region, just this region, and constrained dark matter and said, oh, we are going 0.3. But again, as I told you before, when you are only over here, I could have very different rotation curve later. Although these are large error bars, they still give us some amount of information. And it basically means that I can have, because of this degeneracy, I can have a very different number locally, which may not be the real Milky Way galaxy. So the idea is that you add everything that was pre-Gaia, things over here, maybe not very, very small, and also these regions, maybe there's few things like even one extra point like mass of one region. Okay, that also gives us an immense amount of information. So, for example, if this point, this one extra observation was over here, I would have got a different dark matter than if it's over here. So this very good data with this, even with one extra point helps. And so if you do that, and remember, when Eilers et al. Got this 0.3, again, what they did was that with only, they had to fix the visual matter. So they said, okay, we will take, when they just use this region, the Eilers et al. Data, the results, which is often quoted, when they use it, they fix this, okay, we know the visible matter locally is this, and so we're going to subtract that out. A little bit difference will change your results. So this was previously. Now we see the degeneracies are very, very long. And if I add both of them, this is what we get. The only thing is that because the error bars are very good now, the constraints are possibly the best constraints in the local dark matter. But it's a very, very long degeneracy over here. Again, it's 2 sigma consistent. So the jury is still out, and we're working on the DR3. So this is done with the DR2 data. Coming right over there. So one results are right over here. So this was what was there before. Don't look at this two, just look at this one. Yeah. So this green is not this green. Sorry about that. Yeah. So the color is not consistent across this two. Over there are 2 over here, and this is the. So now, so one thing you can see is that with Gaia, of course, the error bars have come down, and this is probably the best constraints on local dark. But depending on what we believe, there's a 100% difference in the local dark. Okay, so getting density is tricky. Getting velocities are trickier. Okay, so we want to go velocities. So how do you estimate dark matter velocities? Of course, we can directly estimate out of simulations, but we need to simulate the Milky Way, not just our Milky Way. That's very important. Okay. You can use simulations for observations. So in simulations, let's say we decide on simulations, whatever prescription has gone in. Okay, the kinematics of some kind of stars is exactly the kinematics of dark matter. So if we can observe those stars in the real observation, then we can say okay, that mimics dark matter. So that's, again, we have to be reliably on simulations. Or what we can do is that we can try to get it directly from observations, but with simplifying assumptions. So everything has its own pros and cons, but remember, when you are doing directly from observations, we are actually doing it for our Milky Way. And this is exactly where the observations are happening. This is exactly where the experiments are happening. Okay. So here are 2 things that come from simulations. This comes from, this is a velocity distribution of a dark matter inferred from some old stars. And the idea is that these old stars velocity distributions, because they're old enough, are like the velocity distribution of dark matter. That comes from simulations. So you believe what is in the simulations, then you go and observe in the observation, and you look at the distribution of old stars, and then of course there's some normalization. This is what you get. And as you can see, this is the Maxwell-Boltzmann distribution, the black line, and the observations give us this. So it's not exactly Maxwell-Boltzmann. This comes much more prominently in things which come out directly from simulations. Now over here, one concern, or what I would say is that if I was a particle physicist doing an experiment, I want to take the distribution of dark matter, the velocity distribution, and say, okay, I will use it to simulations, then which one should I use? These are all from dark matter simulations. Okay. So each of them are different. Even if we change things, the shapes are different, everything. So let us try to do it from observations. I mean, I went through a little bit of slides because of the students over here. One way to do it from observation is to do what is known as Eddington inversion. Since Sushma has given me 5 minutes, I'm going to skip it and come over here. So this is Eddington's inversion. So there is a unique way of getting, and you can talk to me later, what is it? Depending on certain symmetries of the problem, there's a unique way of looking at the distribution of velocity distribution of dark matter. If I know what is the potential in which the dark matter is moving and what is the density of dark matter. If I know both of them, so the potential, I need to know both the potential of the dark matter and the visible matter. And for the density, of course, I need to know the density of dark matter, which you've already calculated. If I know both of them, then I know what is I can estimate by doing an Abel integral, I can estimate by what is known as the Eddington formula, the VDF of dark matter. And this comes from observations because the potential and the density comes from observations. So this is what the consistent dark matter velocity distribution will be for the distribution of dark matter that is there in our Milky Way. So this is what it is. This is the first sort of distribution, observed distribution, velocity distribution of dark matter using rotation curves. And as you can see, this red line over here, this is different from this halo model that people use over here, especially, and over here. So at the two ends, they are not Maxwell-Boltzmann, and that's what becomes important in direct detection experiments. Okay, so I don't want to go through this. What happens is in the direct detection experiments, the dark matter particles comes and hits you. So you need to know what is the velocity at which the dark matter particle is coming and hitting you. Okay, and so if the dark matter particles are hitting you with larger or smaller velocities, your recoil rates will be different. And so if you are measuring the recoil rates, you need to know what is you have to sort of understand which velocities these dark matter particles are hitting you. And so as you can see over here, if I assume this as the velocity at which the dark matter particles are hitting you, and actual is like this, the recoil rates will change because of this. And so what happens is that for larger masses of dark matter candidates, what happens is it depends more on the mean shifting. That doesn't shift much, so the larger masses do not get affected. But for the smaller dark matter masses, this is the region that affects. Okay, so your constraints on smaller dark matter masses will change from this influences. And to very quickly give you an example, if you recalculate all the dark matter exclusion plots, so this has been given in very great detail, I'm just showing you the final results. For certain experiments, it does not affect. For certain experiments, there's a lot of effect because that depends on what is the energy threshold of that experiment, what are the materials going in the experiment, so you have to basically do the whole thing. But as you can see, for certain experiments, there is a 200% difference in the exclusion limits change by 200%. Okay. This is much more than your error bars or your difference. So these error bars are from uncertainties in your galaxy physics, and the uncertainties that people put in their particle physics models are smaller than this. So the uncertainties that the people have put in, the uncertainty that will come from not doing it correctly is much, much more. This is the new, this is the old. Okay, so important point is that it becomes very, very important and you need to know. And so the phase space is needed to know. Okay, this is for direct detection. What about indirect detection? The indirect detection is more complicated in a certain way because now we need to know the phase space of dark matter all over the Milky Way, not only at our local neighborhood, because photons are coming from everywhere, okay? And so this is what we get in indirect detection. There is this flux of photons. We have something called the J factor. And again, over here, there's a bunch of particle physics and there's a bunch of galaxy physics coming in. 5 minutes information. Okay. So again, we go to Milky Way models. You can see this is the region that's going to give us all the fluxes for the indirect detection. And so we need to know the dark matter over here. And so this one extra point, even one extra point is very important over here. If you just had this thing, you could have got this dark matter versus this dark matter. You won't be able to differentiate. And these two would have given you very different fluxes. And so now we need to have your VDF, the velocity distribution, at different radii. So you can see at the different radii, the velocity distributions are very, very different. Yes, this is all from the data. Yeah. This is all reconstructed from the data. So in fact, if you have three-dimensional velocity distribution, this is what it will look like. Okay. Now, there is more complications. Let's not go into this. And the dark matter distribution velocity. Till now, I'm assuming it to be isotropic. The velocity distribution will be anisotropic. That puts in more complications. I'm not going to, for the lack of time, I'm not going to go into this, but one can calculate if it was an isotropic velocity distribution, how it would be. So what one needs to do, if I want to really have a benchmark model with which I'm going to confront observations, is that to do it very, very consistently. And people don't do this. People do piecewise. And it's not very simple. As you can see, you start with a rotation curve or some kinematic tracers, okay? You build the mass models. Then you include subhalos, okay? Then you include the VDF of dark matter. Now in this VDF of dark matter, there will be a VDF of the dark matter in the smooth component. And for each of these subhalos, they will have their own VDFs. And both will interact, both will have. Then for this VDF, you can assume either isotropy and anisotropy. Then because of the lines of sight, you will have some somorphic enhancement because if you want to put in, or some period depending on what kind of modeling you have, so the velocities are needed. Then you are going to put in all of this together to get a benchmark. And this has to be done self-consistently. So one thing we still need is this addition of clumps. And this is even more difficult. So you could do it from the simulations, but if you want to do it in Markov chain, you have to have an analytic model. So this is what we did. It's a big paper, okay? The whole point is that there are clumps, and this is a fraction of clumps, and this fraction is consistent with what you get from simulations. So these are normalized simulations. What is important to see is that at larger radii, the amount of matter in the clumps at the very large radii is quite large. And so because clumps are concentrated, when you have a rho squared term, which gives you the indirect detection flux, that gets boosted up. And so having clumps is amazing. So this is without clumps, and this is with clumps. Okay, people have been basically concentrating over here, but when people concentrate over here, this immediately tells you that having clumps is important. And now you have to put in the velocity dependence on top of it. So now you can have a velocity enhancement also. So the end of it, you have to look into account of the amount that changes due to the clumps, changes due to whatever interaction you have, and that will be your final J factor. So this is the last slide I want to show is that Milky Way is not the only way. There's one more thing that we want to know. Milky Way is just one of the galaxies. After that, we want to know what is the nature of dark matter. Now, if you just take Milky Way, there is an uncertain error bar in whatever we're getting because it's just statistically one galaxy. So you need to know an ensemble of Milky Ways. And this is what can be done in simulations. So for example, this is a simulation result by Mao et al. Okay, Risa Wishler and Mao, and they did it. This is a halo-to-halo scatter. So these are the VDFs at different radii, and you can see this is the halo-to-halo scatter. And this is an irreducible error that is there, that is uncertain, because Milky Way is just one of these halos. Okay, this is from simulations. This is 10 years old. And now what we can have is we can have it from observations. This is the real halo-to-halo scatter. And this is if we just assume the observations to be dark matter only, and if the observations have baryons. So this is actually the real observations. So now we also have a halo-to-halo scatter on the VDFs. So this now gives us sort of the complete phase space idea of dark matter. We have the phase space due to the baryons in it. We have the phase space due to anisotropy or distribution of dark matter. We have the phase space differences due to halo-to-halo scatter because Milky Way is just one of the halos. And everything is from the observations. Okay. And in fact, as you can see, this is simulation. This is a pseudo phase space density. And the real life where the baryons hit in is over here. And this is Milky Way. Milky Way actually fits right in the center. Very beautiful. Okay. So there's a 3-sentence summary of what I said. Galaxies, the Milky Way, and other local galaxies are wonderful laboratories for the particle nature of dark matter studies. However, you want to probe the nature of dark matter, the particle nature using galaxies, you need to understand galaxy physics and observations carefully before jumping into conclusions. And estimation and careful understanding of the phase space of dark matter in Milky Way and similar halos is the key importance in our quest for knowing the nature of dark matter. So I'll stop over here. Thank you.
Questions? So thank you, sir, for the nice talk. So my doubt is, while you are constructing the velocity rotation, like velocity rotation curve, do you take into account the distortion of Milky Way's disk?
Distortion of Milky Way disk, no. We are talking of the warping of the Milky Way disk.
Yeah, so like, you know, it's not completely a flat system.
Yeah. So typically, okay. So I mean, this answer has many levels. Simplistically, when rotation curves are constructed, you take a plane, you try to see the plane, and you look at the traces in that plane. Okay. Now, of course, in reality, everything is not in the plane. The plane has a distortion. So the distortion has to be there in the modeling. Observations are observations. Okay. So how carefully you look at the tracers, how carefully you're selecting the plane, that is the observations. You try to select the plane as well as you can.
Because as far as I know, like various density profiles, they don't take into account distortion, or are there any profile?
The dark matter density profile comes from simulations. Okay. Yeah. So that does not too much depend on the local wibbling. In any way, density profiles are averages. Okay. The visible matter density profiles, or density is what you assume, you can make it as complicated as you want. The first instant you can assume simplest. Second instant you can put in wobbles in it. You can put in streams in it, depending on how much complex you want. At the end of it, remember, you have a compromise. How much data you have, how good the data is, and how much you can constrain from the data. You cannot put everything in it in theory, because then you won't be able to constrain anything. You need to know what is the amount. So you can try to identify how much error bars that goes. That one can do.
Okay, thank you, sir.
Hi. So do you use the whole Gaia DR3 catalog, or do you select some of the tracers out of it depending upon some characteristics?
You have to select tracers out of it. So this is, first of all, the results that I showed is from DR2 catalog, not with DR3. So we are doing with DR3 catalog. So there are differences that will come up in a DR3 catalog. The DR3 catalog has better astrometry. But yes, you have to select tracers. Now, it becomes more important when you select non-disk tracers, what kind of tracers you want. Different non-disk tracers actually gives you different rotation curves. So sometimes you combine all the non-disk tracers. You also have to be careful, because these non-disk tracers, because you're not doing simple circular motion over there, you basically using Jeans equation, they have anisotropies. The first thing is to basically do, and which I've done actually, is to look at how the anisotropy of these non-disk tracers are as a function of radius, and put that in your Jeans equation.
And just one more. So later, like in DR4, people are going to give a time series data of those tracers. So do you think that would also have some extra information in terms of dark matter velocity phase space?
I don't know. To be honest, I don't know. I mean, probably this time series is too close by. I'm not sure that things will change in that kind of time series.
Okay.
I don't
Thank you.
know.
Thank you.
There is last week there was an IISER conference where one speaker was trying to argue that because these dark matters are fundamentally quantum particles. So therefore, she was trying to argue that if she changes the distribution from Maxwell-Boltzmann to either Fermi-Dirac or Bose-Einstein, there is a 30% difference of the total dark matter abundance calculation. Okay, not all the cases, but in certain cases. I think she was doing something, some special FIMP type of dark matter or something. So in this whole story, does it matter anyway?
No. So over here, the velocity distribution function comes just from the fact that dark matters are is basically is a gravitation, and it's just moving in. So I don't care about what is the particle over here. And the fact that it is not Maxwell-Boltzmann. See, the Maxwell-Boltzmann distribution is it's completely wrong distribution to take. A very simple reason. If I use Jeans equation, then the Maxwell-Boltzmann distribution is a solution for a singular isothermal sphere. Now, of course, first of all, our dark matter distribution is not a singular isothermal sphere. So a Maxwell-Boltzmann distribution is not consistent at all. So That's the first thing that will break you, even if it's only one component. As soon as you put in another component, which is baryons, again, the distribution goes away from the Maxwell-Boltzmann distribution. So this is, yeah, more from the theory side. So this is what is the thing that you should take into account. See, this pseudo phase space, so this is what is plotted, rho by sigma cubed, okay? This is 2021, I mean, people have been doing it for decades now, you know. This is a straight line, okay, very nice. This is just dark matter. So you can see the dark matter, even if it's not Maxwell, this will not give a Maxwell-Boltzmann distribution, by the way, as this thing. But as soon as you bring in baryons, what is happening is that the dark matter particles are moving in an extra potential given by the baryons. So in this thing, the density of the dark matter is giving the potential in which the dark matter is moving. Over here, the dark matter is moving in an extra potential. So you can see this is the effect of the baryons coming over here. And this is what changes. This is not due to just the nature of dark matter, not fundamental nature of dark matter. It's the fact that it is moving in a potential of the baryons. Okay.
Other questions? I had a question. So, so the differences that you get from the simulations in the rotation, in the velocity distributions, particularly for our local neighborhood, you find that the tails are basically shorter, right? So is that within the scatter, or is the difference mainly coming because the simulations are dark matter only here?
Yeah, so I think some of it is what I said, simulations are dark matter only. So if I put in all the simulations over here, the simulations will all be like this. None of the simulations will show this. Okay. So that's where it was simple simulation. So one of the simulations over there is not dark matter only. It has baryons in it. But even that gives you a completely different. So, and as you can, I can show you, yeah. And as you can see over here, this is a very interesting plot. So this is one of the first plot that talk about halo to halo scatter, this VDF, okay, at different radii. This is from Stanford. Right? And over here, this is from the Rhapsody simulation, okay, 96 halos, large scatter. The first thing we did was that to compare it, we did only, this is from observations, but with only dark matter, thinking that there is no baryons, we'll just fit dark matter only halos to it. As you can see, more or less there is an agreement, more or less. As soon as you bring in baryons give a large more scatter over there, okay. And not only the thickness, also the relative heights and widths change. So baryons are very, very important.
Is Rhapsody on clusters, right? Or is this is the Milky Way sample?
They identified halos by mass and stellar mass to be in the Milky Way range.
I see. Okay.
So these are 90 Milky Way size halos from the Rhapsody simulation. Over here, of course, it's not 90 because we had 200 and then we had to take many, many cuts. I didn't get to, we have basically done hundreds of thousands of mock rotation curves to find out what are the reliability galaxies, which can be very reliably talk about. And then we take those galaxies and then over there we have Milky Way-like cuts. And these are like around 20 Milky Way-like galaxies. So, yeah.
All right. Okay, great. So we'll hold other questions till for discussion, and let's thank Shubho again.